So, good morning, everyone. Who else is as hungover as I am? So, my name is Richard Steenbergen, and I'm doing a tutorial on a practical guide to how to correctly troubleshoot with Traceroute. So, I think most people kind of know what Traceroute is. It's the number one go-to tool for doing all kinds of diagnostics. Every OS out there comes with some form of Traceroute tool. There's thousands of websites out there where you can do Traceroute. There's looking glasses, there's visual Traceroutes, there's things that will try to make pretty little maps out of it. There's commercial versions, there's free versions. It seems like it would be a simple tool to use. You put in an IP address and you see a path, and somehow that helps you with your diagnostics. You look at the path and you see where does the traceroute stop or where's the latency jump, and that must be the problem, right? That most people think that that's how this works and that this will immediately help them figure things out. And the reality is it almost never works that way in practice. So the question is, what's wrong with Traceroute? Well, it turns out most modern networks are actually run pretty decently well. So the really simple issues like congestion, routing loops, the things that you would think are most obvious. You run a traceroute, you see the latency go up, and you say, that's where it is. Those tend not to be real issues anymore. So what you mostly see for the remaining issues are the things that are more complex. What happens there is people who just use a very naive interpretation of traceroute turns out mostly to be wrong. So the problem is very few people out there, very few people out there are actually terribly skilled at interpreting traceroute. It looks relatively straightforward and it gives the impression that you know how to read it, but I have yet to find any major ISP NOC that is terribly good, and I still to this day encounter many engineering departments, many people who are in theory very senior engineers who aren't able to read it well. So the purpose of this tutorial is to kind of go through some of the realities behind it, how it actually works, how you can read it better, and how you can troubleshoot networks with it. One of the downsides to people not being able to read traceroute well is most of the time if you go to a NOC and you open a traceroute ticket, most people don't believe you because there's so many false positive reports. So any way to improve that is better. So here's Traceroute at its most basic. All the implementations vary a little bit, but it mostly looks something like this. You have a bunch of lines of output, and on each line you're going to get the hop number. You're going to get the hop DNS, in theory what should be a router along the way. The IP address, really you get the IP address and then you do reverse DNS on that, get the DNS, and you're going to get some type of latency measurement. And typically most standard trace routes are going to do 3 independent probes, and they're going to come back with 3 independent results. So you see here's an example where hop 1, this IP resolves to this DNS, and here's 3 independent probes. But what are you really getting when you do that? So let's look at traceroute, how it actually works at the packet level. So the very first step when you're doing a traceroute is to launch a packet towards the destination with a TTL value of 1. And what happens is every time a router receives a packet and forwards it, it decrements the TTL value. Once it gets to 0, the router drops the packet and returns an ICMP message. So that's step 2. Step 3. Returns the TTL exceed message back to the original sender, the source. That source receives that ICMP, and it knows, it says, I sent this thing out 50 milliseconds ago, and I just got my ICMP back, and so I've now got a measurement of 50 milliseconds. It's the round trip time for how long it took to send the probe out, how long it took to get the ICMP message back. And then it goes all the way back to step 1, but now we start with a TTL of 2. So the packet makes it further into the network. It makes it 2 hops in before it gets dropped. Rinse and repeat. There's a little diagram that shows basically that. You're sending out incrementally 1 more TTL at a time, 1 more TTL at a time. The packet's making it 1 step further in the network, being dropped, and you're getting an ICMP message back and responding and seeing that response and using that to display your result. So, like I said before, Traceroute's doing multiple probes per hop. So, like I said, the vast majority, it's going to be 3. What that is 3 independent probes. So it's in packet 1 that goes all the way through, TTL gets decremented, hits 0, gets dropped, returns the result, and then it sends another packet, and does this 3 times before it increments the TTL. And each probe packet uses a unique key to distinguish itself. So how do you know the difference between probe 1, 2, and 3? So if you look at most Traceroute implementations, the Unix systems, most like Junipers and things like that, anything that's based off that, it's a UDP packet, and it's using a destination port to distinguish itself. So by the time it hits probe 2, probe 3, the UDP port goes up by 1 every time. That's how it knows, okay, this is probe 2, this is probe 3, how to display the results correctly. There's some other implementations out there that use other things. Windows, for example, famously uses ICMP. There's a lot of tools out there that use TCP. Not so much that those are better, but sometimes those will work around firewalls, where some people will just randomly block UDP. But ultimately, the thing to remember is that each probe packet is a completely independent trial. It has nothing to do with the probe packet that happened before. The results are different. The path that it took over the internet can be very different. And what you're seeing is only that last hop where that packet got dropped for each probe. And I'll get into that in more detail later on. So remember, we talk about how you actually see traceroute latency, and this is really important when you go to trying to figure out what's the source of the latency. There are 3 things that factor into traceroute latency. Actually, I'll get to that later. The latency calculation is nothing more than you take a timestamp of when you launch the probe. You take a timestamp of when you launch the probe. You take a timestamp of when you get the ICMP back, and you take the difference. That's your time. Something that people get confused by is they think the routers along the path are doing something to time processing. They're not putting a timestamp in the packet. They're not doing anything special. They're just dropping the packet. It's a normal function of the router when the TTL is exceeded, and they send back an ICMP message. So the latency is always going to be the sum of the time taken for that forward probe to get to that last hop. So however long it takes me to send my probe out to where it gets dropped, the time that it takes for the router to generate the ICMP, which turns out to be measurable, and then the time that it takes for that ICMP packet to get all the way back to the sender. So it's a full round trip. And that's very important later on. So here's some details on the hops that you're seeing. One important thing to remember about Traceroute is that it's going to show you the ingress hop. So here's an example where the first packet goes to router 1 and it has an ingress interface, 172.162.1. When it sends its traceroute result back, it's going to show you that ingress interface. The packet came in over this when router 1 drops it. It's not going to show you the path that it took to come back, that it took to return the ICMP TTL exceed, which is in no way guaranteed to be the same path that it came in on. And it's not going to show you the egress path. So then when router 2 gets it, it's receiving the packet over this interface. It's going to show you 10.3.2.2, and it's up to you to figure out the egress interface from router 1. But everything that you're seeing is every router's ingress interface. You're seeing how it got to that router, it returns an ICMP. How it got to that router, it returns an ICMP. An interesting factoid, that's actually not what the RFC and standard says to do. RFC 1812, which defines this, says the ICMP must be sourced from the egress interface. And if that was followed, Traceroute wouldn't work. It would actually be completely unintelligible for troubleshooting. So that's one of those random people disobey the standard and everyone continues to do it, and that has obvious benefits why. So now we get into one of the first things you can do to really figure out Traceroute is how do you interpret the DNS data that's been put in there. This is how you can do better troubleshooting as you read it. Really, one does not read Traceroute via IP alone. Almost every operator, for their own sanity as well as people on the internet, is putting DNS in there. And the more you can interpret out of it, the better diagnostics you can do. So typically you're going to find in there some type of geographic location, what POP it is, what city it's in, what region it's in, something along those lines. You can pull out, in a lot of cases, the router types and capabilities. You can figure out what type of box it is, if it's a core router, if it's a really low-end edge router, things like that. You can figure out, in a lot of networks with different hierarchies, you can figure out the type and role. There'll be border routers, core routers, and those will have different properties. But the most important thing that you're looking for when you're working with Traceroute is identifying the network boundaries. And I'll get into that more later, but anytime the packet leaves network A and goes to network B, that is potentially, A, it's a point where problems occur, and B, it's potentially a point where Traceroute interpretation problems occur. So, interpreting traceroute locations. It helps if you know the geographical location because that's the first step to identifying suboptimal routing. If you see a packet go from San Jose to Baltimore to back to San Jose, that's probably wrong. And if you see a latency of 100 milliseconds, that might explain it. Whereas if you saw a latency of 100 milliseconds and it went San Jose to San Jose to San Jose, there might be something else you're looking for. So that's why you really want to be able to interpret location. The most commonly used location identifiers, a lot of people do it with airport codes. There's the IATA and the ICAO airport codes, basically a nice globally unique list of airport codes that mostly identify major metropolitan regions. And it gets a little confusing once you start talking about cities with multiple airports or smaller cities that don't have airports, but as a way to identify a major region that matters, that is likely to be a hub of internet connectivity, it tends to work relatively well. The other major identifier is called a CLI code, CLLI. I'll get into that in more detail, but basically you're just, seriously? You're just attempting to identify. Sometimes people will just make up something that they think sounds good. You know, they'll say WAS for a city, for Washington, or just try to take a guess. So the airport codes, like I said, there's good international coverage for almost every major large city, and you'll find lots of good examples out there for most networks. I'd say maybe 75% of networks out there do it something like this, give or take. So examples, SDQ, San Domingo, SJC, San Jose, California. You can go look these all up. Sometimes there's pseudo airport codes. This is where it starts getting tricky for things like New York City, which is served by JFK, LaGuardia, and Newark airports. And some people will actually use those to mean distinct things. This is, our Newark POP versus our New York City POP. And some people will just use, there's codes that represent all of them, NYC, things like that. So that's at any rate, you're understanding that you see NYC and you know that it's New York City. Northern Virginia, similar thing. IED served also by DCA, and so some people just do WDC or WAS, things like that. The CLI codes look like this. So basically, these are full codes that identify very specific telco things. The actual full code looks something like this example, and it's telling you down to a facility and a switch and a rack, and it's mostly used in voice networks. And it's something that's maintained and sold by Telcordia, and you'll see a lot of ILECs and people like that use it. In a non-telco role, most people just strip off everything else, and you're only looking at the first six. It's called the geopolitical and the basically just the state and the city and the state. So again, you can Google all these and figure it out. HSTNTX, Houston, Texas. It's pretty obvious. This is a U.S. standard, so you've got perfect coverage for every U.S. city that matters, including many that don't. And you'll typically see that if you've got like a U.S. network with a lot of cities where you need actual distinction between Baltimore and like the 5 suburbs of Baltimore and things like that. But it's not an actual standard outside of North America. So what you see in some cases is people just fudge this. They'll make up what would be a CLI code, but it's not a standard that you can for sure Google. with 6 letters, you're kind of able to figure out, you know, Amsterdam, Netherlands, things like that. Arbitrary values. Sometimes people just make stuff up. This is probably a huge percentage. You know, you get into example Chicago. The airport codes are O'Hare, ORD, and Midway, MDW. Some people say, I don't know what that means. I'm just going to call it CHI. Things like that. Toronto. A lot of people don't know it's YYZ as an airport code, or YTC is another airport there. So they make things like TOR. And these, you know, they have the best intentions when they make these things. They try to pick things that look right and make sense in English, and you think most people will be able to interpret. And for the most part, you can, but it also gets into situations where there's no actual standard and someone else uses TRN or something like that. So that's, if you're naming your routers, I prefer to stick with something that has an actual convention that you can map to. So I include a table of some of the most common major US cities as far as the internet goes, and the airport codes that represent them. So you'll see a lot of those. The silly codes, so like, you know, NTT is a big user of those, for example. Other more telco-like folks. And then some of the other codes. So between all of these are very representative of the types of things you'll see. And once you get into San Jose, some people will start to do things like SV, Silicon Valley, to represent San Jose, Palo Alto, Santa Clara, et cetera, et cetera. Lots of little cities within a region. The international version looks like this. So these are, you know, as the internet goes, the most important cities. So these are like the representative airport codes, the silly codes, and then some of the other codes that people commonly use to represent them. Good to refer back to if you're looking at stuff. So the next thing you want to get out of DNS is the interface types. The way most networks do this is they'll put their full interface info into DNS. Again, mostly to help themselves troubleshoot, not so much for people on the internet, but if you're smart and you know how to interpret it, it can help you, and you know who to complain to correctly. And if you direct your complaint to the right place first, you'll be a lot better off. So you can pull a lot of stuff out of it. So here's an example, level 3 hop, xe-11-1-0.edge1.newyork1. So here I'm obviously, it's in New York City. I learned the role of the router. It's edge box. That's where they're terminating some of their peering circuits. And you can start to look at the naming format. XE- is Juniper convention for 10 gig. And you can look at, and this changes over time as new line card models come out, but at the time this was written, you know, you could say it's the 11th slot, starting from 0, so it's actually the 12th slot, in a Juniper device that does 10 gig. And you can tell by the numbering, since the last one was 0, that it does at least this number of ports. And you could actually deduce, hey, this was this back at the time was a Juniper DPC with a 4-port 10 gig slot, and this was, no other device could fit that naming profile. So I include a table of the most common interface types and how they get represented. Typically people, there's a lot of, for good networks, automation that comes into this. So SNMP will shorten things down to the short name. It'll turn gigabit Ethernet into GI, and then you'll be able to see those patterns. But you know, you can tell if you see a GI, and depending on the number of fields, if it's iOS, if it's iOS XR, if it's GE-, that's the Juniper Gigi. So you can refer to a table like this and really have an understanding of what the device type is, and then later on what the behavior is for that model, especially as it affects Traceroute, because I'll get into that in more detail. But every router behaves a little bit differently when it comes to how it drops the packet and sends back the ICMP. So the other thing I said you could get out of DNS is the router types and roles. Every network has a different standard, right? You know, what's a core, what's an edge, what's a peering box, what's a customer aggregation box. Most people kind of mostly mean the same things, and you can have an understanding of what those devices are, and then again how they're going to behave. So your typical core routers, they're going to be named things like CR, core, GBR, backbone, CCR, EBR, things like that. Those are some examples from prominent networks out there. But you can get an idea that this is a core device. There's a lot of networks that will do their peering on dedicated edge devices, BR, border routers, borders, edges, IR, interconnection routers, IGR, internet gateway routers. People come up with names for all these things, but you can kind of look at these and figure out this is a peering router. And the other one to look for is a customer router, an AR, an aggregation box, an aggr customer box, a CAR, customer aggregation router, HSA, high-speed aggregation, and everyone comes up with their own little thing, but again, these are the most common ones out there for some large networks. And the most important thing you can get out of it is identifying the network boundary. So like I said, it's important. The reason that it's important is it's always more difficult to, in the order of the slides, those are where the routing policy changes occur. So if it's on my network and I prefer level 3 and I hand it off to this other guy and he prefers Sprint for the return path, and the return path changes the instant it leaves my network. And so by knowing where the network boundary is, you're going to know how the return path was affected, how all the routing was affected, and how that's going to affect Traceroute. And it also tends to be the area where capacity and routing are difficult. Those are the areas where one of us may be paying, one of us may be waiting on the other one to upgrade a peering circuit. And so it typically tends to be easier to fix yourself to yourself than it is yourself to some other third party. And then identifying the relationship, you want to figure out if it's a transit relationship, if one person is a provider to the other, if it's a peer, if it's a true interconnection. It doesn't matter if it's settlement free or not, but if it's routed as a peer, so that only customer routes are advertised to each other, and if it's a customer. And especially the customer side, a lot of networks are very, very clear about where the customer is. They'll put things like .customer, or GW, or they'll put an AS number in the boundary. That's really helpful, and I'll go into that in some more detail and kind of the naming, but that's really helpful because most customer interfaces come out of the IP space of their provider, and probably 80% of the bogus Traceroute complaints that I see are people who send a report to someone who can do nothing about it because the packet has already left their network, gone to someone else, but the IP space came out of their network, and so that's how they got found. So here's an example where it's real easy to spot the DNS changes, and yeah, I'm still using old slides that still have global crossing. Here you can see this was on device AR3.DCA3 and global crossing, and then the next hop it's on Sprint. The other thing you can do is to look for the remote party name. So here in the next example, you see Cogent on a global crossing peer, but it still says gblx.net. What happened there was when the two parties got together and they said, we're going to set up an interconnection between us, one person said, well, I'm going to do the /30 for this. In this case, it was global crossing. And they didn't take the time to say, hey, Cogent, what do you want your full DNS to look like for your router? They just threw Cogent into their naming scheme. So if you look for that third-party thing on the /30, that's how you can tell. And then the other thing you want to do is look up the other side of the /30. So you do a Traceroute, you see hop 5 here, and you say .90. I do simple bit math and know that that's .88/30, so the other side is .89. So do a reverse lookup on .89, and you can see that's the other side. That's the global crossing interface on AR5, which matches up with the ingress interface that you see on hop 4. So now we get into the most fun part of Traceroute, in my opinion, understanding the network latency. So there are 3 main causes that contribute to network-induced latency, the things that you actually see performance-wise on a packet that are going to potentially impact performance, or that are definitely going to impact Traceroute. The first is serialization delay. That's the delay that's caused by the packet moving across the network in packet-sized chunks. As you encode it, transmit it across the wire, pull it back out, serialization delay. I'll go into more detail later. Queuing delay is the delay of the packet sitting on a router, waiting for an opportunity to be transmitted. And propagation delay is purely the speed of light. It's how long it takes the signal to actually flow through the wire and come out on the other end. So serialization delay, like I said, it's the process of encoding the data into chunks. So if I send a 1500 byte packet, you can't start transmitting the packet's first byte until you've received its last byte. So there will be a delay as you chunk it. And the way that the math works on this is the faster the interface, the quicker the process will occur. So it's basically nothing more than convert it into bits and divide, right, or convert the bits into bytes. So if you have a 1 megabit link, that's actually 125 kilobytes per second, and you're sending a 1500 byte packet, do the math, it's 0.012 seconds, or 12 milliseconds of propagation delay across this 1 megabit link. Like I said, it moves as an atomic unit. So every time you hit, mostly this is low-speed devices. So on here's a table that shows the serialization delay. Fortunately, what's happened is the internet essentially transmits almost all 1500 byte packets. It was the max payload size for Ethernet, and no one's really gotten above that. There's jumbo frames out there, but they're not widely used. They're definitely not widely supported. So typically what we've seen is exponential increases in speed with the packet size staying the same. So the serialization delay for modern high-speed networks has gone down into 0.000, doesn't matter, milliseconds. But if you're transmitting this over someone's 1 megabit DSL and you're wondering what the 12 millisecond delay is, that's an important thing you're going to see. And remember also that Traceroute is using small packets. It's using like 64 byte packets, give or take, depending on implementation. But you may see for different levels of performance different results. The next big one is queuing delay. That's anytime the router is holding the packet on the router or switch, holding it in its memory, waiting for an opportunity to transmit. And this is an important one to point out because I think a lot of people don't understand how queuing works and why queuing works. And it's very important when you start dealing with congested links and interpreting Traceroute. So first, a quick word about utilization. When someone says, I'm doing 5 gigs on a 10 gig port, I'm 50% utilized. That's actually not true. What they're saying is it's 50% utilized over some period of time. So that's over the period of 1 second or 5 minutes or whatever the average is on their counter. But at any given moment, an interface can either be transmitting, 100% utilized, or not transmitting, not utilized. And so as the packet comes in, it says, I want to go out this interface. Is it used or not? If it's not used, I can immediately send it. I have no need to queue anything. If it is in use, if it's still transmitting the packet from the previous packet, then it has to hold on to it. And that's just a basic function of routers. So basically, some queuing is going to be necessary all the time for every purpose. Sometimes it gets to be a little excessive, but I'll get into that in more detail later. So again, when is queuing a good thing? When you have mismatched interface speeds. So if you have, for example, a 10 gig client feeding data up to a 1 gig transit link or peer or something like that. Even if you're transmitting 500 megabits, even if by all means the data should fit in the pipe, what actually happens is because the link is faster, because the data serializes faster over the 10 gig, because it comes in faster, the packets arrive faster than they can go out on that 1 gig link, and so they must be buffered. Typically, you see that on a, so the purpose of queuing technically always increases throughput. The longer you hold on to a packet, the more opportunity you have to transmit it. And what happens is as you become closer and closer to being full, as a link gets to like 85, 90% full on a second average, what happens is the amount of time that the interface is transmitting turns out to be very, very high, and the packet has to get queued a lot. So you might have a packet that is perfectly capable of being transmitted. It just has to be held for an extra 5 milliseconds. To get from 60 to 85%. Now maybe you have to hold it for an extra 500 milliseconds to get it from 90 to 95%. And the question is that worth it? Maybe, maybe not, but you need to know when that's occurring on the internet to troubleshoot it in Traceroute. When it's a bad thing, like I said, as the interface becomes more and more full, you're spending more and more time holding onto this packet. You hold onto it for 500 milliseconds, looking for a chance to transmit it, and you very well might, right? You might not see packet loss, but that's where you start to see every packet that goes through the box, or almost every packet, has this noticeable queuing delay. Beyond a certain point, did you really want to hold it for an extra 5,000 milliseconds just to get that packet through from 98% to 99%? Probably not. You probably impacted the application. Most people tend to see internet mixed traffic, the reality, be around 95% is the most they can get through before it starts to be really, really bad. And there's been some presentations on buffer bloat, but what tends to happen is a lot of routers, especially carrier designed routers or routers meant to be bought by carriers, have been built with very large buffers, way beyond and in far excess of what could possibly be needed for reality. And so a lot of routers by default are more than happy to hold on to your packet for 5,000 milliseconds to try and get it through. And unless you go configure that down and go configure your queuing differently, you'll still see that behavior a lot on the internet. And the third form of latency is propagation delay, the time spent on the wire. So really the math here is pretty straightforward. It's the speed of light. So if you want to know how the math works for fiber, fiber is made of glass. I have a tutorial on that also, but it's two forms of glass. It's a core and a cladding, and what happens is they have different refraction indexes. The light hits it, bounces back off the cladding, stays in the core, and it just propagates along. And it's propagating through glass with a refractive index for fiber of around 1.48. So that means it's traveling at about 0.67 C, about 0.67 the speed of light. So roughly 200,000 kilometers per second is how fast it moves across the wire in fiber. So 200,000 kilometers per second, you can turn it into 200 kilometers or 125 miles per millisecond. Real simple math. And then divide by 2 to take into account the round trip time, because remember Traceroute is showing you forward and backward. So as an example, a round trip around the equator of a perfectly straight fiber route, what would the point of that be, through a lot of ocean, would take 400 milliseconds just from the speed of light delay. So if sometimes gamers complain, they say, I want it to be faster, and you say, take it up with God. So then the question becomes, how do you identify what latency is affecting you? You start by looking at location identifiers. You look to see if the routing is as expected and if it fits in the propagation delay. So here's an example of something going from NYC, New York, to LHR, that's London. So there's a difference of 67.6 milliseconds, and that happens to be a 4,200 mile route. Sounds about right, actually. There's another example where you see the latency shoot up from, you've got WDC on hop 7 here, AT&T, and you're still in IED, that's also DC, in hop 9, and yet the latency is shot up 220 milliseconds. That's probably not speed of light related. And the other thing to remember is no one lays their fiber out straight. People tend to run their fiber on paths to go to major cities and populations. And so it will never be as perfect as a perfect scenario. You've got repeaters, region, the slack loops, the fiber goes through all these different places. But this gives you at least a ballpark of doing the math and seeing, does this make sense for the latency that I'm seeing? So the next big thing we get into when we're interpreting traceroute results is prioritization and rate limiting. And remember that I said the traceroute latency is the sum of the time that it takes for the probe packet to go out, the time required for the router to drop that packet and send back its ICMP, and the time for that ICMP to get all the way back to the source. So numbers 1 and 3 are real network characteristics that affect real packets, including things that are not traceroute packets. Number 2, on the other hand, is only affecting traceroute packets. This is a behavior that the router typically turns out not to be very good at doing. I'll get into that in more detail, but number 2, if there's any type of delay in the router's ability to drop the packet, generate an ICMP, and send it out, that's going to cause traceroute to look bad even though network performance is fine. So there's a lot of conditions that can cause this. You can hit rate limits on your generation of your ICMP message, causing artificial loss. So you'll see loss in the middle of a trace route, and you'll think that there's a problem, and there might not be. And the router can be slow on the generation, and that causes artificial latency. So to understand that, we have to talk about the architecture of a router. So modern routers have distinct forwarding paths, so different ways that packets get handled as they go through the box. So the data plane is what it's called when the packets are going through a router. The router's doing its job. It's routing, millions of packets per second from point A to point B. It's shipping it via the data plane. And even inside of a data plane, even inside of a modern box, fully ASIC enabled, doing millions and millions of packets per second, there's a fast path and a slow path. The fast path is anything that can be handled well in hardware. It's the ordinary shipping of packets. And the slow path is anything that's an exception packet. So it's examples of things that cause exception packets. If you have IP options on the box, if you're trying to do source routing through IP options, if you require ICMP generation, so that's the important one for Traceroute. If you have the box configured to do logging, anything like that, what tends to happen is the packet actually gets punted to a CPU to handle this stuff. This is stuff that's relatively complicated and isn't just as simple as look up an IP address in a table, figure out a next hop interface, and ship it. And so even on a modern box, all of these boxes with their very high-end line cards have a little CPU sitting on every one, and it's doing this type of stuff. And then the control plane is the packets that are going to the router. These are control protocols, so your BGP, your IS and your OSPF, your SNMP packets, your CLI access. When you're logged onto the box, all your SSH and Telnet stuff is going there. Anytime you ping the router directly, anytime the router's doing ARP, so every default gateway, every .1, every time you type IP address blah, that's an entry point to the control plane on the router. And a lot of router CPUs out there are horribly underpowered. So this is not uncommon to this day to see very high-end, multi-hundred gigabit devices with an old 600 megahertz MIPS or PowerPC CPU. And typically, even the best, highest-end box with the newest routing engine is going to be 3 to 4 years behind whatever's available out there for PC, because people are building these as industrial applications hardened against temperature, and they're just slow to ship new ones. And remember, ICMP generation is not really a priority for the router. That's a nice to have, but ICMP generation doesn't make the packets flow. So on a lot of boxes out there, like old Cisco iOS boxes, there's an infamous process called BGP scanner. And the way that iOS works is every 60 seconds it has a little process that walks down the routing table and checks to make sure all the routes are still valid and pulls things that it doesn't. Basically, the symptom here is on some platforms, the slow path data plane, the stuff that is doing the exception generation for, I just dropped a packet, now I need to send an ICMP, is shared with the control plane. So you tend to see things like someone churns BGP, and all of a sudden you get a traceroute spike. It can even be something as simple as someone from your NOC logs into a box and types a big, expensive command, the box is calculating it, and traceroute latency spikes. That's typically not found on a lot of the higher end boxes. They'll have a dedicated control plane and slow path data plane. But even on things like 6509s, which are still hideously common, it's the same resource. It's the same CPU that's doing it. And so if it's busy doing one thing, it's not doing the other. So the most famous example of this is the old Cisco iOS BGP scanner. Every 60 seconds you see a spike in traceroute and you have no idea why. The other big one, again, is rate-limited ICMP generation. Even in the slow path data plane operation, there are many reasons for an ICMP generation besides TTL exceed. There's lots of everything from destination unreachable because the route didn't exist, because you're going to a host where ARP hasn't been resolved yet, to packet too big. There's dozens and dozens of reasons why a packet would get dropped or an ICMP message would need to get generated. And there's no such thing out there as a traceroute ASIC. It'd be nice. No one's done it. No one's put any effort into making it really faster. So you've got a general purpose CPU that's generating ICMP as a not critical function, and the routers are typically, they have two choices. You can either process all the ICMP as best you can until it takes down your other services, which is bad, or you can rate limit them and try not to take down those services, but affect traceroute. So remember, it's actually relatively easy to cause a TTL0 denial of service. It's something as simple as a routing loop. You turn up a customer, you assign them a /24, you route it to them. They haven't actually installed it on their router yet. They have a default pointing back to you. You just created a routing loop. Some worm on the internet sends one packet. It loops between the two of you forever. And every time that TTL0 is hit, it's generating ICMP. So if there wasn't a rate limit, this would actually be a big denial of service vector for routers. So most routers are going to put an artificial rate limit on this. And the reality of this is the rate limits tend to vary wildly, not only by vendor, by platform, by software revision, by individual line cards, by models of line cards. And in a lot of cases, they're not easily configured, logged. You have no idea if you're hitting them, and you have no idea if you hit them on FPC 7, but FPC 8 is fine. And all it takes is, one of the common traceroute tools out there that does repetitive traceroute over and over and over is MTR. And people will, oh, look, I'm firing up MTR. I just left it running for 6 hours, and it's been sitting there sending traceroute packets over and over. You get a couple of users doing that, and all of a sudden, you start to hit some of these baked-in limits. So you need to figure out how you can tell the difference between the cosmetic loss in latency, the things that are just traceroute specific, and the things that are actual forwarding issues. And the secret to that is if it's an actual forwarding issue, the loss or the latency will persist across all future hops. So here's an example, hop 2, you see 18 milliseconds, 18 milliseconds, 68 milliseconds, oh no, the world's ending. Well, actually not, because it goes away in hop 3. So that means that it was purely a function of the ICMP generation. If it was affecting all packets, you would see at least 68 milliseconds or more persist all the way through in the next hop. Sometimes you need more probes to figure that out for sure. But if you see a latency spike in the middle of a traceroute, it means absolutely nothing. If you see loss in the middle of the traceroute, it usually means absolutely nothing. But those are, again, a huge source of people opening traceroute-based tickets. I saw a drop somewhere in the middle. That didn't mean anything. At worst, it could be the result of an asymmetric path. It took a different path to come back, and it doesn't really matter. But more often than that, it's an indication of just artificial rate limiting. You see a delay like that, or the box was busy on that particular control plane at that particular time. So a good way to test that is if you're very concerned, if you think that maybe there's something wrong with this interface, try a non-TTL expiring method. And again, this is control plane, so it's going to have different performance. But try just pinging the interface and see if you see that loss persist, or if it's just something that's happening from ICMP generation. So the next thing we get into with Traceroute is how do you troubleshoot all these asymmetric paths? So remember, Traceroute is only showing you the forward path. And remember, I showed it only shows the ingress interface of how the packet went there. It shows you absolutely nothing about the return path. But the return path is a half of the latency value at the very least. But it's completely invisible. You have no idea. And the only way that you will ever know about it is to contact the person on the other side and say, can you please do a traceroute back to me? And even that is a guarantee of absolutely nothing, but it's at least a place to start. So that's the real hazard of traceroute is it's completely hidden. It can be completely different in every path. And as one person without any cooperation from the other side, if you don't have a looking glass on that side, if you don't have a customer who can do a traceroute back to you, you have half the information that you need, and you're trying to make a determination. So the only way you can confidently analyze a traceroute is to have it in both directions. And a lot of NOCs that get traceroute tickets, source and dest, source and dest, source and dest. Always ask for that. And even then, like I said, you can't catch all the potential stuff. But now we'll talk about some of the details of that. So asymmetric paths, I said before, start at network boundaries. That's where administrative policies change. So here's an example of a trace route that's going from DCA 3 Global Crossing, we know that that's DC area, to Ashburn Sprint Link, also DC area. And those are both actually like Equinix Ashburn. So as it goes from this one particular router on Global Crossing to this one particular router on Sprint, you see a 100 millisecond spike in latency. So now you ask yourself, what could be wrong here? It could be congestion on that path. That particular link could be full, and it could be exactly 100 milliseconds worth of queuing that's happening, things like that. It could also be an asymmetric reverse path. So as we see, once the packet crosses the boundary, once it hits Sprint, Sprint is now in control of how it sends that return path back. It's going to have its own routing table, its own policy, its own peering policies, its own local pref, all of the above. And it's going to vastly affect what path gets used. And a good cue here that that's what's happening is it's consistently 100 milliseconds, like precisely across all things. Typically, if it's congestion, you're going to see some variance there as TCP backs off and things like that. So when you see exactly 100 milliseconds, you start thinking, maybe it's the reverse path. So how do you work around asymmetric paths like that? The most powerful thing you can do as an end user sitting here working Traceroute, trying to figure things out without magically being able to get the other guy on the phone and do 1,000 Traceroutes for you, is to control your source address. So here's an example. Say you're multi-home, you're an ISP, you're buying transit, and you're connected to two networks that are now the same thing, Global Crossing and Level 3. So you know that Global Crossing reaches you via Global Crossing. And it so happens that Sprint, because of their different policies, they reach you via Level 3. So that's how you start to say, maybe the reverse path is between, is going over Level 3, and that's the issue. How can you prove that without having access to Looking Glass and all the routers and all the endpoints? One thing you can do is to run a trace route on your side from your router sourced from your /30. So the way that almost every ISP works is when you connect as a customer, they give you the /30, the interface IP, out of their IP space. And that's IP space that's owned by them, routed by them, part of their supernet, and it's going to be routed that way. So you do a trace route, and you manually set in your traceroute command the source address to be that Global Crossing /30. You're forcing the return path, even once it hits Sprint, to come back via Global Crossing. So then you can look and see if that affected your results. If it did, try it on your Level 3 path. Oh, look, you now see 100 milliseconds on everything. So you know the path, the issue in that previous example is the return path coming back in over Level 3. Now we get into some more complicated stuff. Asymmetric paths with multiple exits. So remember, asymmetric paths can happen anywhere, and they do. And in fact, the way the modern internet works, they happen pretty much everywhere. Turns out there's no terabit Ethernet yet. Sorry, Randy. So people tend to splay things out over, it's not uncommon to see 64 by 10 gig paths. It's not uncommon to see many, many, many different parallel paths happening. And so all these asymmetric routes are happening all the time as traffic is load balanced. And networks interconnect with each other in multiple points. So here's a very simplified example of a major network with 3 locations, San Jose, Chicago, and Washington, D.C. They interconnect with each other in all 3 points. And remember that in almost all examples, peering is done via hot potato routing, closest exit routing. So you want to get the packet to the other network as quickly as possible because they know more about routing it than you do. So in hop 1, we see an example where the outbound packet goes out a Washington, D.C. interface and comes back in, that same interface, very simple. Hop 2, we've now incremented the TTL by 1. We've sent the packet through Washington, D.C., the little red line. It goes out to Chicago. Chicago drops it, sends its ICMP back. But the return path that Chicago sends is via the Chicago interconnection. So if, for example, there was congestion there or something about that path was broken, you would see the latency spike for that hop. But then by the time it hits hop 3, by the time the third packet, the green line, goes out and it's made it 3 routers deep and it's hit San Jose drops it and sends it back, it's got a different path. So every point along the way can have a completely potentially different asymmetric path with all these different exits. So sometimes you'll see a latency spike in the middle that's caused by that and not caused by the cosmetic stuff. And that's where you kind of have to ping all the interfaces manually, one thing at a time, and really deduce one thing after another to figure out what the real issue is. So then the question becomes some more advanced troubleshooting with source address. What happens if, you know, it's a peer address, or I'm the transit provider and the /30 is numbered out of my space? Well, you can still get some benefits by playing around with it. A lot of times you'll see different results just by different hashing. So for example, if you have a router and it's .1 and you do a traceroute source from that, and the hash that gets calculated from that address sends it down this path, and you do it from a different interface on your router with a different hash in a way that gets calculated differently, it's going to expose different paths that you weren't seeing before. And there's a lot of examples out there where people will be reporting intermittent loss and you won't be able to figure out why. And it's because your particular traceroute just happens to be sourced from you know, using the hash that just sends it over the clean path, not the broken path. So the more things you can try, the more likely you are to uncover those types of issues. Another thing to remember when working with Traceroute is, where is your source address coming from? Most routers, Cisco, I don't know, XR, most classic boxes out there set the source address to the egress interface that was used. So if I'm sitting on a router and I do Traceroute 1.2.3.4 and it goes out my level 3 interface, it's going to set my source address to that level 3 interface. And Juniper is going to do that by default too. But they have a command, system default address selection, that forces it to use the router loopback. In a lot of cases, that might be more what you're looking for. So for example, if you did that traceroute out level 3 and it was sourced from level 3 IP space, that might not be exposing all of the different return paths that are coming from your real IP space, from your real customer who's really multi-homed with you. So again, try all those different things and take that into account when you're looking at your paths. So the next fun thing about Traceroute, multiple paths and load balancing. So remember that I said every probe is an independent trial. And UCP and TCP traceroute probes, like I said, are using a different port every time. And the ICMP stuff may use some other method to encode that. But what's happening is, whenever there's multiple paths on a link, you've got 4 by 10 gig, and they're not done as a layer 2 bundle. It's not an LACP bundle. It's done as 4 independent links, and you're trying to do layer 3 hashing across them. That's called ECMP, equal cost multipath. And what happens there is you tend to see multiple hops show up at every point. So here's an example of a link that's clearly multipath going through Telia, where for hop 6, 2 of the probes landed on BB2, and 1 of the probes landed on BB1. And this, you know, they're routers that are probably sitting right next to each other, and traffic's being evenly distributed across them. And what Traceroute does is, when it encounters a different return address than what it got in its previous result, it just displays it like this. It says, here's another result that we got. And so people have to know how to interpret that. You see that a lot on the internet. Of the 3 probes, 2 go over one path, 1 goes over another. Very simple. Now we get into some more complex examples. Here's old Vario DNS. Here's an example of a packet going through what used to be Vario, NTT. And you see the first hop is an Ashburn. And then hop 5, you see some very different load balancing. You see New York and Chicago. And a naive person might look at that and think, oh my God, my packet just went in weird ways, the wrong direction. We have no idea what's going on. What's actually happening here is it's being load balanced between 2 paths. One that goes New York, Seattle, and one that goes Chicago, Seattle. So again, that's completely harmless, but if you are a naive user looking at Traceroute and you don't know how to interpret that, you're going to come up with the wrong results. Now we get into the really painful stuff. Unequal equal cost multipath. So that's an example where it's load balanced across 2 equal paths, but one happens to have more hops than another. And it makes the paths look like this. So here's an example of load balancing where X got inserted in the middle. And what it does you get traceroute results that look like hop 3 has hop 2's result in it. And so people get real confused by this one. They go, it's going back and forth. I don't know what's going on. It's out there. You'll encounter it. You have to look, and when you see, hey, I'm seeing that same hop, that's tends to be an indication that you're seeing that. So when in doubt, you can eliminate the whole thing by just doing a single probe. So your standard Unix traceroute implementations, the command is -q1, and so instead of sending 3 probes for every hop, it's going to send 1. And if you're confused and you don't know what's going on, send 1 probe, look at that path, and then send it again. See if it comes up something different. But again, remember, every probe is still an independent trial. So just because in this one example you see a return that says this, that in no way means that's the path your flow went over or anything like that. So when you're working with Traceroute, you're looking at many different variants and how to interpret all these results to build a complete picture. And like I said, one way to try out different paths is just to increment the destination IP or the source IP by 1. So if you're tracing to a customer and they're .123 and everything looks fine, try tracing to .124. See if it changes the path along the way, and see if it changes it in a way that breaks something in the middle, because that's a common thing that you'll see as the different IPs get hashed differently. And now MPLS and Traceroute. How Traceroute behaves when you put it on an MPLS network. So there's a lot of large networks out there who operate an MPLS-based core. In fact, most large ones at this point. And a lot of them out there, they run it in such a way that their core devices, their core label switching devices, don't even carry an IP routing table. And in fact, like the Juniper PTX isn't even capable of doing it. It's a dedicated MPLS only box, and so that's fine for tracing, for delivering an MPLS packet. Then the question becomes, if you want to show that hop, you have 2 choices. You can either completely hide the hop, so MPLS gives you the capability to turn off TTL decrement, so you can magically make the packet go from point A to point B and hide all of your network in the middle. Some people do that just to make traceroute shorter or not confuse people, and some people don't because you're actually trying to figure out what's going on inside your network. But when you've got an MPLS only box and you are trying to show that hop, you need to figure out, where am I going to send that ICMP back? And if you don't have a routing table and you can't do that lookup, you've got a problem. So one common solution to this is something called ICMP tunneling. What happens there is, if you generate an ICMP on the inside of an LSP as it's being forwarded through a network, rather than have that router immediately do a lookup and send it back to the source, the router puts it back in the same LSP that it got it from. And the packet continues all the way to the end, pops out there, and then routes. So it makes it work, but it makes Traceroute look really weird. So here's the details on that. Throw out your previous example of how Traceroute works as you increment through hops 1, 2, 3, 4. What's happening now is router 1 sends its ICMP message all the way down to router 4 before returning it to the source. And here's what it looks like. Here's an example of AT&T doing it. So you see a packet sitting in Global Crossing Palo Alto. It hands off to AT&T in San Francisco, and you say, oh no, the latency just went up 72 milliseconds in San Francisco. Is it a congested link? No. What's happening is that San Francisco packet, and then the Chicago packet, and then the New York packet, everything there is going all the way down to that very last router in New York before the return message can come back to you. So that's why you see every path, every hop along the way has 74 milliseconds. That's usually the indication that that's happening. If you see something, the latency is precisely the same, or precisely the same as you can get going through all these different hops all the way to the edge point, you're inside of an LSP and you're seeing ICMP tunneling. So try not to freak out over that. Really, final thoughts on Traceroute. Before beginning a Traceroute for any type of serious analysis, always ask for forward and reverse, source and destination paths. Someone sends you a Traceroute and they take out 3 lines in the middle and they send it to you. They've done almost nothing for you. make sure your NOC knows, make sure anyone that you talk to knows, make sure when you send in a Traceroute complaint yourself, you don't get snippy and say, I've already done all the work and here's the 3 lines that matter. Send the source and destination IP so people can actually troubleshoot it. Beware of snippets of Traceroute of missing information. And also remember that users running a Traceroute towards an IP they saw in another Traceroute is where things tend to go south. So a user might Traceroute to www.yahoo.com, and they get 3/4 of the way there, and they find a Yahoo router, and they say, I'm going to Traceroute to that Yahoo router. That's a completely different forwarding characteristic than the end host. So you really need that real destination IP. You can't just look at those IPs in the middle and try to make your determinations. And that is my tutorial on Traceroute. Questions? Anybody? Mike, so it's on the recording?
Can't get to a mic, you can see me, Raz, but this is Randy. So I Traceroute to my host in Seattle, and from that host I Traceroute back here. Am I seeing the full return path that kind of corresponds to the way things would have come back from there, et cetera? And what am I learning? How much is it worth doing?
So you're not guaranteed that you're seeing the full reverse path, but you're much more likely to be assured that you're seeing something much more similar to what that path would look like. So he's saying, I'm doing a Traceroute to him in Seattle. He does a Traceroute back to me, back to my actual end user host where I'm communicating from. That is the best way you can eliminate all of the different things out there and really get the route. This is how the packet got to me. This is how my packet got to him. This is how his packet got to me, with all the disclaimers of multipath, hashing, all of those things that can, maybe that Traceroute packet went down the clean path, and maybe the real flow that's been broken has gone down the broken path. But you've eliminated most of the issues that you see are around the policy change, where the IP address crosses into Sprint, and so suddenly their routing policy changes, their reverse path changes, and you can't see it. And if you can get the guy on the other end to do that Traceroute and send it back to you, it's a much better place to start from. It's eliminates 85–90% of the issues that you'll see right off the bat.
I'm wondering about the current slide, how to read it. Does it mean that starting with the hop number 3, we have this MPLS tunneling? And can I say that it's that all the devices, maybe up to hop number 9, are MPLS tunneling devices, or?
Yeah, so MPLS is used by large carrier networks to move the packet from point A to point B. And so what's happening here is there's an LSP that's taking the packet from this router in San Francisco to that router in New York. But because they haven't turned off TTL decrement, you can still see all the hops along the way. So what's happening is hop 3, after it does its Traceroute and it says, I'm dropping this packet here in San Francisco, I need to return my ICMP, it's not doing a routing lookup, finding the source address and sending it back. It's putting it in that same LSP going all the way to that original destination. So yeah, you're seeing all the router paths along the way to that final destination. And once it hops out at the end, it routes all the way back, but that explains the latency.
So this is the same for number 4 and so on. So this number 4 is the same thing and so on.
Yes.
Okay. Thank you very much.
Yeah.
Hi, Matthias from DKIX. I was wondering, some new Traceroute tools have this additional option. It's called Paris.
Which one's that one? I forget.
So I was thinking it has to do that they try to change port numbers and stuff like this so that they enforce different ECMPs. Do you have any details on that?
Yeah, I should have mentioned that. So, like I said, the more you can change the port numbers, the more you can vary the probe, the more likely you are to encounter all the different paths out there. So there's many different Traceroute implementations out there. One, obviously, Paris, that we'll try to build that in. So as it does multiple probes, and to some degree you get this out of MTR too. If you leave MTR running, it's basically just like top for your trace route. It sits there and repeats over and over and over. Every time it does it, launches a new probe, potentially exposes a new path. So if you leave an MTR running, you'll tend to see all of those. And there's other tools out there that I'm not familiar with all of them, but as a way to kind of go out and find all those different paths, yeah, change up the destination ports, source ports, everything.
So, and the second question, so sometimes you see, and even in your presentation, some trace routes give back some MPLS labels. Do they help you with any debugging?
Do I have any examples of that? I meant to throw that in there. So there's when MPLS came out, there was a big question of how do we communicate MPLS information back in a trace route, and so there was an extension. Basically what happens is you can encode some amount of information in the ICMP message as you send it back. When you send the return packet back, you send some of the original packet. So take it back to an example. I launch a probe packet. It's 64 bytes long. I stick some piece of information in the header. You know, I know the source, the dest, all that stuff. When the router drops that packet and sends its ICMP back, it copies the first bit of that message. And in doing that copy, it can also include MPLS information. It's not terribly helpful for anyone outside of the ISP network, and it's actually not even helpful for that. It's basically telling you the label number, which you're not really going to do anything with unless you are troubleshooting an MPLS implementation that's broken. You pretty much have to be the carrier on the network looking at it to see, but some Traceroute implementations will be able to interpret that and display an actual label number as it goes through, or you'll be able to see the stack depth. You'll be able to see if it's inside of 2 LSPs or 3 LSPs. For someone on the internet, not on that network, it's essentially pointless. Andy?
I'm Randy Bojaj again. Regarding exploring different hashing, et cetera, if anybody's interested, just write to me and I'll point you to our ICMP Internet Measurement Conference paper from a year ago, where we actually looked very heavily at using ping with ID manipulation, just as Traceroute does, to explore paths and find out how radically, crazily different they can be. What's worse is on the same physical fiber with people, because you can't get a 100 gig interface from Ashburn to Dallas. So you take 10 of them and you lag them. Radically different times if you can explore those different fibers in the lag. So be careful. For the kind of stuff we as operators do, you're close enough for government work. For the kind of things researchers do, you better know what you're doing with ping. And we saw like 30% differences on the same path, on the same fiber.
I would hope not to see that. Not on the same fiber, but a lot of times what will happen is someone will take 10 gigi circuits or 10 by 10 between Ashburn and Dallas, and they'll get it from 3 different carriers with 3 different fiber paths, and they'll treat it the same internally. You'll load balance across all 3 and all of that, but one will be much higher than the other. It's really rare to see that big of a variance on the same path. You'll see some, and that's why you have to do hashing. You can't just ship every packet down with a perfectly even load balancer. You'll see reordering, different fiber cable lengths, different things like that, different queue depths on every interface. But a lot of carriers out there are mixing and matching. You know, you go out and you buy whatever the cheapest path is at the time, and you, in some ways, load balance it with a longer path and a shorter path. Yeah.
Hi, Joe with Info Relay. Our help desk is really smart, so we ask for forward and reverse MTRs instead of trace routes from customers, and then trust that they can get it. But you made an offhand comment about that banging on the CPU of every intermediate router in between. Are we being bad net citizens when we do that?
Maybe. So I'll give you an example, and I thought I had more details in here, slide-wise, on some of the different hard-coded limits, but you know, and again, this depends greatly on router vendor and software and things like that, but there are a lot of boxes out there, a lot of boxes still deployed where there's a limit of like 100 packets per second per line card for, you know, an 80 gig or a 40 gig line card. And so it doesn't take much. It takes, you know, 10 gamers and 3 guys in the NOC running MTR, and all of a sudden you've got enough packets coming through that you're now dropping TTL. And what tends to happen is the more people that do that, and the worse it gets, the more people fire up Traceroute to figure out what's wrong. And so, yeah, you can very easily get, you know, 100 gamers are all pissed off that their server rebooted. They all fire up Traceroute, and now you just broke more Traceroute for a lot of people. Just make sure that they keep in mind, don't leave it running forever. Really, the bigger fix there is talk to your router vendors and ask for better handling. And we've started to see more and more of that over time. So one of the things I didn't get to put in here is Juniper, as of I think 11.4, pulled all of their ICMP generation rate limiting out into a standard structure called DDoS protection, misnamed. But and you can actually configure it and you can log it. So you can see on FPC 7, I'm hitting this limit, and that's why I'm not returning traceroute packets, and you can actually bump it up. But for a lot of boxes, for a lot of legacy deployed systems out there, it's hard-coded, it's per line card, it's per version of OS, and you have no way to change it, even if the box is perfectly capable of doing more than that. Anybody else? Behind any pillars? All right, well, thank you guys very much.